Okay, guys, so today we're going to talk about the late Paleozoic part of the history of the Earth. The late Paleozoic is going to cover quite a bit of time, but just like the early Paleozoic, the further back we go, even though there are a lot of fossils from these times, honestly, the less we know about it. So anyway, we've got a lot to get through, so we'll go ahead and get started. So this is the period of time that we're looking at. And again, we're starting looking at the Precambrian and this purple piece down here, which really isn't to scale at all, going to about 542 million years ago. And we already covered the early part of the Paleozoic in the previous lecture. So I'll get my little pen here and kind of mark what we've already done. So we already talked about the Cambrian and all the way through the Silurian and what's going on with geology through there. Now, today we were talking about the Devonian up through the Permian, taking us to the Great Dying, the biggest mass extinction event ever, right here at the very end of the Permian, paving the way for the evolution of the dinosaurs. But I don't want to get too ahead of myself as far as talking about life on Earth. There's a whole other class that will deal with that, but we will talk about life for the rest of the semester as well. But that's just to kind of give us a perspective of what's going on. So not quite getting to dinosaur times yet, but we are definitely getting into a very fascinating world too. So a little bit about the late Paleozoic evolution of North America. The trends that we're going to be seeing through this time is going to be, first of all, a lot of carbonates. So we're going to have a lot of limestone dating from the early half or so of the late Paleozoic, so from the Devonian, and then the first half of the Carboniferous, which is called the Mississippian period. Then things are going to change. We're going to start to get some new climates and some new organisms showing up, which will form coal. So we're going to get a lot of swamps and a lot of clastic sediments forming coal interbedded between sandstones of river deposits. Then things are going to dry out as the continents are moving closer and closer together and beginning to form Pangea, which will happen at the very end of the late Paleozoic, at the very end of the Paleozoic era, ending the Paleozoic world. So because we're starting to form a huge supercontinent, the inside of that continent is going to dry out. It's harder for water to make it all the way to the interior of a large continent, especially when climate is very warm. And so we start to get some of the first major desert conditions to show up since life evolved on our planet. So we're going to get evaporites forming like salt from desert environments. We're going to see a lot of sea level changes. The Paleozoic is marked by a lot of sea level changes, partly glaciation. So as continents have moved further south, and encircling the South Pole, like Africa and South America, Antarctica, Australia, and India, all continents of Gondwana, those are going to start to get glaciers, as we saw with the end of the Ordovician period, where we had glaciers growing once we had a continental mass big enough to support ice sitting on one of the poles, again, the South Pole. So that's going to continue to happen, and as glaciers grow, sea level tends to drop. And we're also going to get, as Pangea comes together, we are creating a huge supercontinent, and that also tends to overall mean sea level also decreases. So we'll see what's going on there. The image I have here is kind of a good one to imagine, at least through the last half of the late Paleozoic, where we get the first forests. We get the first plants that are capable of producing a really tough material that's going to allow them to grow very large, wood or lignin. So we're going to get the first major woody plants and the first forests on our planet. And those forests will be really interesting. They're going to do some really cool things. And okay, so what's going on during the late Devonian period? So here's our paleogeographic image here. We're going to have a lot of mountain building going on. So we see Laurasia. Again, this is where North America would be. So Cincinnati would be probably right about here, but the United States is rotated. So this is the East Coast, and then up into like New England and stuff. And then if we had Florida, which Florida's not even thought about yet, it'd be hanging off of probably down here. So we're forming the Acadian highlands here, one of the major thrusts of the Appalachians. We have this ocean here called the Iapetus Sea, and it's going to get smaller and smaller between Laurasia and Gondwana. So we're having these mountains being built, and again, another thrust of the Appalachians. The Iapetus Sea is closing, and on the west, we're also forming the Antler Highlands. We're beginning to form the beginnings of the Rocky Mountains. We could still see mountains of the antler orogeny in the state of Nevada. So what's going on then is because we are creating so many mountains, we are eroding away those mountains. So in between those mountains, we're going to deposit all that sediment. So lots and lots of clastic sediments in between them, adding onto the landmass of the continent of North America. So the erosion of these highlands produced vast amounts of red sediments. In Northern Europe, this is going to be called the Old Red Sandstone, and in the Eastern U.S., it's called the Catskill Delta. And throughout the Devonian and the other periods, we can also see some of these red sands in Kentucky too. The red sand that makes up Red River Gorge National Park is going to be from the Pennsylvanian, so a little bit later, but similar idea. When we have mountains building nearby, that sediment's got to go someplace, and it's going to be dumped on nearby land masses. As Gondwana moved over the South Pole, extensive continental glaciers formed, and for the early Carboniferous, at least for the Mississippian period, sea levels rose and fell. So Gondwana began to collide with Laurasia, so the Iapetus Sea is continuing to close more and more as Gondwana is getting closer and closer to Laurasia, and this set off a series of orogenies worldwide. So we have an orogeny going on here, we have some going on here. So we have a lot of mountain building during this time period. One of the plants that we begin to see covering the land are gymnosperms, which are seed-bearing plants, like our all of our, so not flowering plants, we're not there yet, but things like pine trees, juniper, cycads, stuff like that. So those plants are beginning to spread over the land. And then for the last part of the Carboniferous, and we also call this the Pennsylvanian period, we are going to have continued mountain building. We're forming the Ouachita Mountains down in Arkansas. We're forming the Allegheny orogeny, which is going to be the final thrust of the Appalachian Mountains. And we're also beginning to form some more Rocky Mountains. So we have some ancestral Rockies forming and lots of coal swamps worldwide. One of the reasons why we have extensive coal swamps is because temperature was largely, pretty warm, but mostly, we don't necessarily need warm temperature to form forests. We've got lots of cold forests today, and did back then too. We just have a lot of trees, and so this rock, coal, is a biological material. So, I know this is an Earth history class, we're not focusing too much on life, but it's going to be impossible to talk about life on, or geological history of our planet without also talking about life. So we have all these forests forming, and as those trees die and begin to decompose a bit, but we have a lot of pressure, they're going to turn into the vast beds of coal. So this is called the Pennsylvanian period because, from the rocks that we often see, or from the state that we often see rocks of this age in Pennsylvania, which of course have contain a lot of coal. These coal swamps are going to become the source of most of the world's coal supply. So China is going to be down here as well and forming a lot of coal. Kentucky, so any place that's relatively close to the equator, but, we can have coal swamps even at colder latitudes. We are forming coal beds that are going to end up moving around as the continents move around and become worldwide. Oh, here's China. Yeah, so we have some North China going on here, South China, yeah, perfect latitudes to have those vast coal swamps forming. Finally, at the very late Permian period, so this is going to be the very last period of the late Paleozoic era, we are finally suturing together Pangaea. So Gondwana and Laurasia collide together, they form Pangaea, and not just do we have a huge supercontinent, but this also means we're losing that Iapetus Sea, and we're forming a huge mountain system, the Central Pangaean Mountains, which are essentially the Appalachians. So this is the final thrust of the Appalachian Mountains, and They're not going to get any taller after this point. They're just going to be eroded down, and some uplift happens later, but we'll deal with that later. They're largely being eroded. This is the last time we have an orogeny that contributes to the building of the Appalachians. If we have one supercontinent, we basically just have one ocean, and that's called Panthalassa. This is the global ocean that surrounded Pangaea. And water temperatures then were pretty equable because of the increased freedom of circulation. If water can get freely from the pole to the equator and back again, it's going to be all pretty much the same temperature worldwide. Oceanic circulation becomes much more, warm water here, cold water here, when we have many different seas and the continents are pretty far apart, as we have today, where our cold water currents and our warm water currents can freely move from one place to another, but only through certain conduits because of the position of the continents. But during this time, we just have one big sea, so temperatures are pretty similar wherever you are in the ocean. Not a bunch of difference there. The size of the supercontinent and high mountains from the previous orogenies, including this one, the Appalachians here, means that we are going to have dry conditions. So we get deserts. So much of the central part of Gondwana here, much of, getting especially 30 degrees north and south latitude away, which is today known as our desert latitudes. Those are going to create some of the first deserts on our planet since life evolved. So it's a good thing we just had something very special happen previous to this, and that is going to be an adaptive radiation that allows reptiles to begin to live in dry places. And we'll talk about that at the end today. So it's a good thing that happened because, something that has to lay its eggs in water, like amphibians, like frogs and toads, fish, stuff like that, wouldn't really make it in a desert. We need to have, a very special way to reproduce where we can get away from the water. We'll get into that a little later. So these dry environments produced extensive red bed and evaporite sequences. So we get red beds, which are highly oxidized bits of sand, lots of sandstone here, and coal forming as well as salt. Evaporites will be the salt. And then coal formation zones are becoming more restricted. So we kind of go from coal to more and more desert deposits, including those dunes from forming red beds and evaporite deposits like salt. So lots of salt deposits in the world during this time. So again, kind of a review over the paleogeography for the late Paleozoic. We have major glacial cycles, largely over where much of Gondwana is at the South Pole and is covered by glaciers. So that's the fact that we have glaciers growing and shrinking and growing and shrinking means that sea level is going to fluctuate throughout the entire world. And that's going to affect the entire world. That's going to affect the life of the whole world, especially marine life. So we start to get, so we could tell that we have a very highly variable climate because we know there were coal swamps, there were evaporite deposits and other bodies of rock indicative of deserts, and also something called tillites. And tillites are bunches of sediment dumped at the edge of a glacier. So we know there were obviously glaciers too. So lots of different things going on with climate throughout the time period. And then again, at the end of the Permian, Pangaea is forming, and then here's a little picture of Pangaea again, with that big mountain system right in the middle and a bunch of deserts on either side of it. So this is going to dramatically alter ocean and atmosphere circulation patterns. The growth of mountains and the building of a supercontinent really affects climate worldwide, and definitely did so during this time. So I'm bringing this picture back up from our previous presentation over the early Paleozoic Earth history. And so we already talked about the Ordovician or Cambrian, Ordovician, Silurian. So we talked about the orogenies that I'm hiding here. So the Tippecanoe, the Sauk, and the Sauk sequence, the Tippecanoe sequence, and the Taconic orogeny. And we're seeing what's going on during this time period. So between the Devonian and the Permian. So we mentioned the antler orogeny briefly, just a little piece of the Rockies that are beginning to form during the Devonian period. and that's in the west again. So this image is nice because we're going from west to east. So what's happening with the Appalachians though? Oh, we're building on a lot of stuff. So we have the Acadian orogeny, we have the Ouachitan orogeny forming the majority of the Ouachita Mountains, and finally the Allegheny orogeny, which forms right about 250 million years ago, right at the very end of the Permian, and as Pangea is finally sutured together. We'll get into these others later for the rest of the, lots going on with the Mesozoic. That's where the Rockies are being formed. But we're starting to form the baby Rocky Mountains, at least here at the late Paleozoic. Some of the sequences that we're going to see covering the land will be the Kaskaskia sequence and the Absaroka. So these are going to be conditions where sea level is going to be sufficiently high to cover the continents and deposit a whole bunch more sediment. So so we're also building some mountains here too. The Absaroka Mountains are near where I lived in Bozeman, Montana, and are exquisite. They're just beautiful, much of Wyoming too. So we'll talk about the sedimentation that's happening during this time. Okay, so first of all, the Kaskaskia sequence. So this is happening in much of the kind of the Midwest, the northern part of the Midwest. So this is a large packet of rock units overlying the earlier Tippecanoe sequence that we talked about in the previous presentation. Its base is marked by a major unconformity where we've had erosion occurring before this sea level then rose high enough to deposit more sediment. So the Kaskaskia sequence began accumulating as the sea, called the Kaskaskia Sea, transgressed or rose over the North American craton, which was quite low. There's really no mountains in the middle of the North American craton. So as sea level rose, it fills in much of North America, as it has many times, during the Middle Devonian and then the late Mississippian period of the Carboniferous. The base deposits are made up of a quartz sandstone made up of eroded material from the Appalachians. So again, those Appalachian mountains here are eroding. That sediment is being dumped, and because those rivers move to the west, not south as they do today, but in this case they were moving to the west, and actually it was more like northwest because the whole continent was rotated around the other way. But anyway, so those rivers are depositing a whole bunch of sediments. So bits and pieces of the Appalachians can be found under, Illinois and Missouri and Iowa. And then as we start to get into limestone, though, that's becoming more oceanic deposits, so some shallow marine sediments here, as our sea is covering much of the Midwest. So this is what it looked like during the rise of the Kaskaskia Sea. So we have, again, sediments made up of the eroding Appalachian Mountains, and also any sandstones that are older from the Cambrian and the Ordovician here near the Ozark Dome. Where's the Ozark Dome? I'm not seeing that. Okay. And the Canadian Shield is also going to be exposed too. So wherever we have sediment or rock that is high and dry above the sea, it is likely then to be eroded and then dumped into that sea. And then here's the Caledonian Highlands, and some of this is going to break off and become Scotland. So Scotland wasn't that far away back then. We're also going to form some black shales happening too, and that means that we're going to have, we'll look at a map of the black shale plays a little bit later, but we're going to start to form, shale that is organic enough, has enough carbon in it to actually produce some levels of petroleum. But many of the rocks that are forming here are actually carbonates or limestone, and there is a lot of reef building going on during this time. Okay, so some of those black shales, here's the black shale plays. So everything that's in kind of purple are where we see black shales from this time period, the Devonian. So this shows us the extent of the Upper Devonian to Lower Mississippian Chattanooga Shale, which is a very extensive body of rock. And then we see the New Albany Shale as well, but the Chattanooga Shale is where we would call it around here. And it's a very famous body of rock because it's where we see a very cool group of animals called the placoderms, or the armored fish, like one called Dunkleosteus. So this is a drawing of what Dunkleosteus actually looked like. This is a huge fish, the biggest predator of its time. And this is a picture of the skull at the Cleveland Museum of Natural History. So it's also black. It's the same color as the rock that it's found in. And so this is pretty cool because this is a very special fish, and the Devonian period is known as the Age of Fish, partly because of the development and diversification and just absolute dominance in the oceans of these armored fish that capture the imagination because they look absolutely terrifying. They're not sharks, by the way. This is, the sharks during this time are kind of small and they're nothing terribly special, but this is actually a type of bony fish that's more closely related to probably the lobe-finned fish, the fish that would give rise to animals that walk on land, the tetrapods. So this might actually be sort of a distant relative of us, actually, more closely related to us than they probably are to sharks. So we can have scary fish without them being sharks, that's for sure. Definitely true in the Devonian. So beginning into the Middle Devonian and continuing into the Late Devonian, we have shales and some coarser clastic sedimentary rocks replacing those carbonate deposits that we previously had. And so these are also going to be, the source is going to be from the rising mountains of the Acadian orogeny, which extend up into New England as well. So again, as these sediments are, as these mountains are breaking down, that sediment's going to be dumped, and some of that will start to make up, a lot of like sandstone and siltstone, but the shale is going to be from places that are pretty anoxic. So we think that there were these anoxic environments, and that's where the black part comes from, where there's plenty of carbon, but oxygen didn't really get to react with that carbon, so it remains as a black color. And that's where the petroleum tends to come from. So fossils are quite rare, though when they do show up, they can be pretty cool. So this is a picture of the New Albany Shale. This is actually an exposure of it. I believe this picture, this is the Button Mold Knob Quarry in Kentucky. I got to visit some what we call the Chattanooga Shale, New Albany Shale, whichever, around Lexington. I don't think it was when I was at WKU, and I collected, I don't have a picture of mine because it's in a display case at NKU, a pyritized brachiopod. So we get some of these seashells like brachiopods, and if they were, it was not like this when it was alive, it was just normal, seashell. But because it was it died and then was covered over in a very anoxic environment, then pyrite, iron sulfide, can survive and ends up replacing the calcium carbonate shells. So we don't exactly know how these black shales form, but they were definitely on the bottom of, a part of the shallow sea that doesn't really have a lot of oxygen, which means anoxic. Not a lot of, and we know that because there's not a lot of bioturbation. There's not a lot of mixing up of the sediment, which you could probably tell by these really fine layers. Finding that in the oceans is pretty unusual, and it often indicates not a lot of life there because there's nothing burrowing through the sediment to really dig it up. The shales contain large deposits of uranium and petroleum. And, when we do find fossils, they are, they can often be replaced, at least partially, by pyrite and some other cool minerals that form in these special situations. So that's kind of a neat type of rock. Here's the shale plays. So they're in red. And one of the ones that's very well known in Ohio and has been used for petroleum is the Marcellus shale. And we are also seeing a lot of the sedimentary basins here too. So the whole kind of blue area is that sedimentary basin where we find this shale, and then where we've actually gone through the effort of pulling petroleum from the shale. So of course, in order to, we're not talking about oil flowing out of the ground like Beverly Hillbillies or anything like that. In order to, if you don't know what that is, that's fine, you're not missing much. But in order to get the oil out of the shale, it requires fracking, which is often kind of controversial and stuff like that. So basically you have a rock that's very, very fine grained because it's shale, it's mud, and there's sufficient organic material in it that if you're able to get that to liquefy using heat and pull it out, you can get some petroleum. So that's, you know, kind of the idea. And that's where a lot of petroleum in the United States is coming from, is from these oil shales from this time period. Okay, so as we continue through into the Mississippian period, now we're getting into our carbon, oh, sorry, that picture, I may have to change something. I think this picture is the same as the last one. I think I maybe screwed something up. Anyway, that's okay. So after the black shales formed for the beginning of the Mississippian period, now we're going to start to get new carbonates resuming. So all of this is carbonate bottom, and the Kaskaskia Sea is going to regress, and now that limestone is going to be exposed to weathering and erosion. So we end up with a huge unconformity where there are some carbonates deposited, but then there's a period of erosion, and it won't be until we get another sea showing up where we get renewed deposition of sediment on a large scale in the central part of the continent. So another body of rock, the Absaroka sequence. So we talked about the Kaskaskia, now the Absaroka. This is going to be from the early Pennsylvanian period, which is the last half of the Carboniferous period, to all the way up to the early Jurassic. So we're going, you know, into the Mesozoic for this. So again, at the bottom is, you know, unconformities because we had extensive erosion before that. And rocks are going to be quite different from one side to the next. So we have non-marine rocks in the east, and coal as well, to more marine sedimentary rocks and even limestone carbonates in the west. So we get very different rocks in the east or the west, from the west. This is an image of the Absaroka mountain range outside of Wyoming and in Montana as well. So very cool mountain belt. There we go. There's a better image. So what's happening during that time then is the lowermost sediments of the Absaroka sequence are confined to the margins of the cratons. That means the edges here, where we have some of the oldest sediments going on. They're going to be thickest in the east and in the southeast, right as the Appalachians are rising and the Ouachita Mountains are rising as well. And then as we go westward, they get thinner and thinner. So we're seeing lateral changes from non-marine sedimentary rocks here in the east, where we have, again, sediment from all these rivers coursing their way down off of the Appalachian Mountains and then being deposited in the sea that covers the western half of North America. Yeah, so we're going to transitional environments and then even offshore environments where we even get into some limestone further west. So definitely changing some conditions here, and sea level is low enough that, yeah, while we do have a lot of sea, the Absaroka Sea over top of North America, we still have a lot of rivers that are moving and depositing sediment further west. And that's, of course, a terrestrial environment. So a little bit more about that coal now that we're in the Pennsylvanian period again. So we're kind of going, you know, first of all covering paleogeography, then going back into more detail with each of the periods, and then as we talk about life at the end, we'll, you know, kind of do the same thing. Start from the Devonian and yeah, go back. So through the Pennsylvanian period, which is the last half of the Carboniferous period. So why do we call those different things? So in Europe, they were fine calling it Carboniferous because the whole period looked like it had a lot of coal. So it's like, okay, let's call this the Carboniferous, which means coal forming. That's great, easy. Geologists started to look in North America and found out that, well, actually, for the first half of this period that you call the Carboniferous, there really wasn't much coal being produced. There was still a lot of limestone. So the first half of the Carboniferous, then we in the United States, and I don't know how universal this is, it might be more universal than I think, but at least we in the United States call it the Mississippian, and that indicates a lot of limestone. Much of the limestone in Kentucky is Mississippian aged, and that's down south central Kentucky, you know, where Mammoth Cave is. That's all Mississippian aged limestone. And then the second half, and named because many important limestones from that time period are found in the state of Mississippi. And then the last half of the Carboniferous then does have coal and is named for Pennsylvania. So we take the Carboniferous period, split it into Mississippian and then Pennsylvanian, And so some of those words you might see kind of interchangeably, but just rocks are different in different parts of the world. That's all it comes down to. Okay, so anyway, you got a chance to kind of see this image. I know there's a lot going on here, but this is talking about how coal forms. So coal forms in vast swamps that are formed from the invention of wood. So plants are using this molecule to create tougher bodies, harder bodies that are going to be stronger and get taller and taller. So the first trees are able to evolve during the Devonian and then definitely into the Pennsylvanian. We are forming vast forests. And as those trees die and fall down and break down and squish together like what's happening over here, there's some heat going on. So the vegetation turns into peat, which is still very woody. If you found peat, there's all sorts of plant material in it. But then over a period of time with more heat, it will actually squish even further and turn into coal. And there's definitely different grades of coal too, based on how much heat and how much pressure that material had undergone. So coal formed during a very special time in Earth history. The time we're usually dealing with is between about 300 to 250 million years ago. Not quite this huge span like they give here, but closer to 300 to 250. So during this very special time in Earth history, do we have tons and tons of wood that's building up, but this isn't happening today because we have plenty of organisms today that could digest wood and break it down. So we're not forming coal today, and we haven't done in about 100 million years on a large scale, at least 100 million years on a large scale. So coal formed during a pretty special, unique time in Earth history. And so all the coal that we use today, and China uses, and England used to start the Industrial Revolution, it's all from that one special period in Earth history where plants reached to the skies, pulled sunlight and carbon out of the atmosphere, use sunlight as energy, and then were buried. So coal is essentially buried sunlight and buried energy, and that's why it contains a lot of carbon. And that's why as you burn it, it's a hydrocarbon. It produces energy when you burn it. It's kind of the point. So that's a little bit about how coal functions and why it's a very special material. Of course, though, since all those coal swamps formed, what those trees were doing, like I mentioned, is they were pulling carbon dioxide out of the atmosphere. Ooh, if carbon dioxide is removed from the atmosphere, what kind of things might we expect, right? We would have a reduction in the greenhouse effect. We might expect the climate to get cooler. That's what happens, and that's one of the things that is thought to have caused the largest mass extinction event our planet has ever seen, is those millions of years where trees pulled carbon dioxide out of the atmosphere, weakening the greenhouse effect. And that took place over 100 million years and caused a huge cooling event. Well, what if we took all that same carbon from deep underground, threw it back up in the atmosphere in only 150 years, as we have done since the Industrial Revolution? We would expect that same carbon then to add to warming because we are emphasizing the greenhouse effect, right? Not too surprising to geologists that that's exactly what happens, and that's how carbon contributes to warming. So we're taking that buried carbon, throwing it back up in the atmosphere in a far, far shorter time than it took to be buried in the first place. So anyway, but that story of coal will come back again, not just to talk about modern climate change, but to talk about that big extinction event at the end of today. Okay, so here we go. So as we're talking about coal, we are also talking about something called a cyclothem. So this is going to be a cycle of repetition, mostly due to sea level. So cyclothems are common in Pennsylvanian age rocks and are very repetitive. So we're alternating deposition of shallow marine sediments with non-marine sediments. And so we're seeing episodes of sea level rise, transgressions, and sea level fall, regressions. So again, that's a trend we're seeing all throughout Earth history: sea level rise, sea level fall, sea level rise, sea level fall. What is that doing as far as deposition goes? So we can go from a few different environments. If sea level is very low, as it is over here, so this would be low, that blue line is kind of showing us what's going on. Low sea level, high sea level. When we have low sea level, we have erosion taking place, but as sea level rises, so sea level is going through a transgression in this case, so this would be called a transgressive sequence where you're going from non-marine or terrestrial sediments to coal, which is usually transitional, to finally marine and offshore sediments. That means sea level in that one location, and this is usually global, is rising over time. So non-marine sediments, more transitional, and then finally marine sediments, that means sea level has risen. So we go from a period of time where erosion would take place because our landmass was high and dry and experiencing erosion to a period of sedimentation with rivers, finally a swamp right at the edge of the sea, and then near shore, and then finally offshore environments. And then we see the opposite happening where we're getting more land and less sea as we have a marine regression and we go from more offshore or marine environments to more and more terrestrial environments to the point where we have an unconformity, in this case called a disconformity, where we have lots of erosion going on. So this whole series of sea level rise and fall is called a cyclothem. And these are found all over North America from this time period because not that sea level rise and fall are unusual at all, it's just that coal is a good marker because that is happening right at the edge of the sea, usually in swamps. Think about where swamps exist today. Florida Everglades, for instance. Great example, perfect example of where sediment and water makes its way to the ocean, and the swamps are the buffer between those two realms. Okay. So when we're looking at environments that produce cyclothems, here's a good example. So this is a reconstruction of a Pennsylvanian coal-forming swamp where we have, landward areas. So we'll have some erosive stuff going on, not much going on just on land here, but we also have rivers coursing across the land, depositing some sediment. We have a delta covered by a swamp, which is going to form coal. And then we start to get into offshore and then finally out at more open sea marine environments. This is a picture of the Okefenokee Swamp in Georgia, really good example of a modern coal forming environment, though of course not on the scale of anything from the Pennsylvanian period, but it is similar in a lot of ways. So cyclothems often contain, marine invertebrate fossils with the marine interval ended by an unconformity. So as we start to get the oceans rising again, we have an unconformity going on there. Non-marine sediments will overlie the marine sediments, though in a lot of cases, due to the speed at which this may happen, or erosion or non-deposition can occur at any time, cyclothems may be missing one or more of the typical units. So it can be a little bit more complex than we talked about in the previous slide, but there's a lot of neat stuff going on there. All right, so that's a bit about our sea level rises and falls in the center part of North America. What's happening more toward the edges of North America? That's where our mountains are going on. So here is one of our orogenies. This is going to form some of our ancestral Rocky Mountains here as we have the antler orogeny occurring, and we're forming the front range of the Colorado Rockies. So some of these are going to be a little bit later into the Mesozoic as well, but we are starting to build some of those ancient Rocky Mountains surrounded by sea. So where we see some of this is the Garden of the Gods near Colorado Springs, Colorado. I got to visit this years ago when I lived in Bozeman, Montana. I got to take a horse trail ride through the Garden of the Gods. Very beautiful and very cool scenic area, and I had no idea what was going on geologically. I was, studying dinosaurs. I wasn't talking about this sort of thing, but it's pretty cool. So there's a lot of deformation happening during the Pennsylvanian period, and the greatest deformation was going on in the southwest and formed the ancestral Rocky Mountains. So all these igneous and metamorphic rocks dating back to the Precambrian era were uplifted, that they were eroded. We have some ancient sedimentary rocks from the Paleozoic that had already been deposited, also being eroded. So we have all these sands then That's what this is, sands and conglomerates being deposited in surrounding basins. So we have uplift, we have erosion, we're dumping new sediments, and that's what's forming the Garden of the Gods sedimentary rocks. So these are, these would be far younger rocks than we have here in much of Kentucky. So we're forming lots of red sandstones, and they'll be uplifted later. This uplift didn't occur until the Mesozoic and other orogenies associated with the Rockies, but during this time, the sediments were actually being deposited, a little bit further down. Okay, so here's what we're seeing during the Permian then. So now our basin here in the interior of the North American continent, or craton, is being filled in with sediment during the late Pennsylvanian period. The Absaroka Sea is slowly retreating from the craton, so that by the early Permian, the sea extended from Nebraska to West Texas. And that's about it. So it was getting much, much smaller as sea level is dropping, and more of this craton is being exposed. And a big reason for that is that we're getting closer and closer to Gondwana, and we have sea level dropping. So glaciers are growing. We're starting to get some orogenies in the east then that are going to contribute to and build Pangea. So we're drying out, and continents are starting to rise a little bit higher. By the early Permian, which is the next period of time, the sea, so we get all these evaporite deposits. So there are some barrier reefs here. These little plus signs mean evaporite. So we see salt. And during the Permian period in Texas, Texas is one of the best places to find some neat fossils from the Permian. We are getting lots of deserts, lots of really dry deposits happening here. So check it out. The craton is completely drying out, and our sea is being lost. It'll come back though. We'll have a sea again later on. So this is called the West Texas Permian Basin, and so we are surrounded in our little basin here's Texas by some reef systems going on, and I'm not sure why it's called the Delaware Basin. That's kind of weird, but we're getting into New Mexico, and so a lot of there's a cool national park here. This is Capitol Reef National Park, but that's further north. That should also be the same time period. I think it says on the next slide, Capitan National Park, something like that. Oh, we'll see it in a minute. But we have a pretty complex, span of lagoons, barrier reefs, and open shelf marine environments formed in West Texas and southern New Mexico. So this is why we have a lot of oil production from this area, is because reefs and other shallow offshore marine environments are places where a lot of algae, which is what's going to form petroleum, collect and can develop oil. So that's also an organic type of rock like coal, but obviously largely liquid and formed from algae instead. Both are formed from plants. Here we go. So this is, the Capitan limestone is what this body of rock is called here in Texas. This is a reconstruction of a reef from the Middle Permian period from the Capitan limestone, and an image here of the Guadalupe Mountains in Texas. So some of the animals that we see, again, all animals, we're not looking at a bunch of plants here. These are some big sponges. So lots of sponges during the Permian. We're also seeing some bryozoans, some brachiopods, some coral. Have a few fish going on here because by the Permian we have I don't want to say modern fish, but we have a big diversity of different kinds of fish. Those armored fish of the Devonian are long gone. They go extinct at the end of the Devonian period, and we're starting to get some groups of fish that we have alive today. The Guadalupe Mountains are, this is the Capitan limestone at the top, and it's forming the caprock of the Guadalupe Mountains. It's rich in fossil corals and associated reef organisms, so this really shows us what the reef used to look like. And of course, it's part of Texas now, as you could tell from the vegetation here and the fact that you can actually see the rock is a desert. It's very, very dry, and yet you can pull up all these seashell fossils and see this used to be coral reef. Okay, the antler orogeny. So this is an image of the reconstruction of the Cordilleran mobile belt during the early Mississippian period. So we have deep water continental slope deposits are being thrust eastward over shallow water continental shelf carbonates or limestone, forming the Antler Highlands. So we have this thrusting occurring, so a big thrust fault going on here. So this rock would either not move much or maybe move down a little bit. This rock is being thrust up over top of it, forming the Antler Highlands, and again, the ancestral Rockies. All right, so we're starting to get some mountain building going on. For the Ouachita orogeny, back headed east now, so going into Arkansas. First of all, we have some depositional, so this is our depositional environment where we have a shallow sea going on, forming some sedimentary rock here. Then we start to get a continental collision between North America, which is this body of rock, and Gondwana, this body of rock. And so we start to get volcanism and therefore mountain building growing on Gondwana during the Mississippian period. This continental collision continues during the Pennsylvanian and the Permian, and eventually, as Pangea comes together, it is final. But the Appalachians are going to do some stuff too. Okay, so this is what's going on in the Acadian and the Caledonian orogeny. So the Acadian orogeny is what we generally tend to call it as we're talking about the Appalachians. The Caledonian Highlands, though, are going to be the part of this that breaks off and becomes the Highlands of Scotland and the majority of Scotland. So it's going to move away quite a bit. So this is a block diagram showing the area of collision between Laurentia and Baltica. So that happened previously as Laurasia is being built together. And so we can see this Catskill clastic wedge that we talked about a little bit before with the old red sandstone and the old red sandstone here, which is going to be a big part of Scotland. And one of the things, if you remember back to James Hutton, and I'll go back over this a little bit, but remember those vertical beds of sedimentary rock overlaid by the more horizontal beds that James Hutton saw at Sycamore Point? That's what's happening here. So it's forming here many hundreds of miles away from what would be Scotland. And here's those vertical beds of sedimentary rock. Here's the deposition of the old red sandstone on top. This is going to head over and become a big part of the east coast of Scotland. So it's pretty cool to think about how these continents used to be much closer together, and and now they're broken up and kind of assorted all over the globe, which is kind of cool. So here's an image of the old red sandstone. This is in Devon County, England, and during the Middle Devonian, we have weathering of the highlands, and that's what's producing the old red sandstone. So this is going to be weathering from the surrounding mountain belt. All right, so that's pretty much it as far as geology goes. Now we're going to back up a bit and talk about life in these places. So just, again, one slide per each period. So in the Devonian period, again, this is known as the age of fish. Plants are going to continue to take over the land as they started to at the very end of the Ordovician into the Silurian, but they develop woody tissues and they develop leaves. And leaves do a lot of things because leaves help to, help with photosynthesis, a lot of surface area there. They also retain moisture, and as long as there's like a waxy covering, then they help prevent moisture from being evaporated away. So plants are really, doing a lot of stuff during the Devonian period, and they're also beginning to create thick soils, and those tend to bury carbon. And we see that repeatedly throughout Earth history. Whenever plants develop a new thing, as they only did about 30 million years ago too, but we'll talk about that later. Whenever plants develop the ability to grow faster and faster and hold onto more soil and grow more efficiently, they tend to build thicker beds of soil. And that means that carbon being pulled from the atmosphere, because that's what plants do, they bring in carbon dioxide and they're leaving it as they erode and create soil in the ground. They're pulling CO2 out of the atmosphere. So we can expect some cooling to happen, and that's exactly what goes on at the end of the Devonian. So the end of the Devonian occurs, and we lose all of these awesome armored fish like Dunkleosteus and a whole lot of animals. So we have, and plants too. So we have a major extinction event at the end of the Devonian period, largely due to glaciers. And there's some continental reasons for that, but a big reason is because plants are pulling carbon out of the atmosphere. So life forms have created climate fluctuations many, many times, and something we understand pretty well, helping us again to understand what effect humans can have on today's climate. Whenever plants go through some really big evolutionary changes, what follows right behind? The things that rely most heavily on the plants, and that's often going to be teeny tiny little guys, usually the arthropods. So arthropods are going to be, here that we're talking about on land, generally are going to be the insects, the scorpions, spiders, centipedes, millipedes. In the oceans, we're also talking about things like lobsters and crabs, the crustaceans. There's still trilobites during the Devonian. They never quite reached their Cambrian levels of diversity, after the end Cambrian extinction event, especially after the end Ordovician extinction event. But trilobites persist through the rest of the Paleozoic. Insects are finally going to evolve, as a response to all the new food that they have to eat because of all the plants. So insects are going to show up and begin to dominate the land. In the oceans, of course, here we go, are jawed, bony fish, and still a lot of jawless fish, like this guy, Boreolepis, I believe, Bothriopus, I'm sorry. And then this guy over here, another jawless fish. And this, of course, is something like Dunkleosteus. There's a few of the big armored fish, but he's probably the most famous. Then, what's happening that's very special to us, the first tetrapods evolve. So we have a picture here of Tiktaalik. This looks like Ichthyostega, or no, sorry, this looks like Ichthyostega. Anyway, you don't need to worry about what those guys are, but these are going to be, tetrapods are all the four-legged animals. They don't all have four legs. We're a tetrapod, for instance. So tetrapods are going to be the amphibians. Modern amphibians are squirrels, oh my gosh, frogs and salamanders. Back then, definitely no frogs, really no salamanders. Amphibians during the Paleozoic are not really quite like any amphibians we have today. In fact, calling them amphibians may not be the best thing to do, but anyway, that's what we do. So, but we're going to start to get the first tetrapods. So we get things that have kind of this lobe-finned fish. We have this lobe-finned fish like this guy here. And they are going to begin to develop hands and a shoulder girdle and a hip girdle and a neck and eyes on top of their head, kind of a flat head. Those are all characteristics of animals that are beginning to walk on land, like Tiktaalik here. So yeah, kind of an amphibious type of creature. Tetrapods then are going to include those, the reptiles, which we'll get into here at the end of the Paleozoic, the mammals, and the birds. Those are all tetrapods. And yeah, I know birds have two legs, but they've got arms, it's fine. So any vertebrate animal after fish, any vertebrate animal on land basically is a tetrapod. So it's not important really because we're not dealing with life evolution in this class, but I will be using that word again. I just wanted to go ahead and define it. I thought that'd be a good idea. So in the Carboniferous, again, we're splitting this into two major periods, the Mississippian, which this top image, should have made at the bottom because of geology, but anyway, this top image here is showing us what it would look like during the Mississippian, where we have these vast meadows of crinoids. So we have this type of echinoderm or starfish relative. We also call them sea lilies, and we do have them alive today. They're definitely animals. And they're filter feeders. They're just kind of stalked, hanging onto the seafloor. And so during the Mississippian, they become very common all over the place. And after the Devonian extinction event, it takes a while for reefs to begin to build again. But they do. Through the Pennsylvanian, we start to get some more reefs. But most Pennsylvanian rocks, because sea level was becoming quite low, are going to be coal swamps. So we start to get huge, diverse forests with lots of wood, lots of, plant materials. And another thing that happens too, as we pull carbon out of the atmosphere, well, or not we, but plants, as plants pull carbon out of the atmosphere, they're also creating what? Oxygen, right? Plants take carbon, use it to build their bodies, and then they pump oxygen out into the atmosphere, just like the stromatolites did a long time ago, right? So that's what plants do. That's what photosynthesis is all about. So because we have all this vast woodland, we are going to create a lot of oxygen in the atmosphere, up to about 30% oxygen in our atmosphere during the Pennsylvanian period. That's crazy. That's right now we have 20% oxygen in the atmosphere, so that's even more oxygen than we have today. That means that insects and this like millipede or centipede type of guy, which are not quite insects, but yeah, they're arthropods, so that's fine. It means that arthropods on land, which breathe air through their skin, they breathe oxygen because they're animals, that's what animals do. They breathe oxygen through their skin, they can grow much larger. So we have these huge, big old dragonflies, we have, millipedes the size of alligators. So when you see like ancient, I don't know, like paleo art with a dinosaur and like a big, meter wingspan dragonfly, it's not the right time because this is where we have the big, 3 foot long or 3 foot wide wingspan dragonflies and other huge insects, not dinosaur times. Dinosaur times experience a lot of conditions, particularly atmospheric conditions, very similar to what we see today. Okay, and then something very special happens, the most special thing probably in the evolution of our ancestors, the first amniotes. This is going to be all the tetrapods minus amphibians. So what an amniotic egg is basically referred to as a pond within a shell. It's an egg that has enough moisture and a protective shell that it can be laid on land. For example, our modern amphibians, frogs and salamanders, they can live on land all they want, but they have to still lay their eggs in the water. And when the babies are born, they're little tadpoles, right? They are swimming in the water and they develop, go through metamorphosis, and then they become adults eventually and all that. But they have to live near water generally in order to reproduce. The first amniotes then we can kind of refer to them as reptiles. Reptiles doesn't really mean anything though, it's just an assemblage of amniotes that we don't really know what to put them in. So anyway, don't worry about that. Our dinosaurs class deals more with what reptiles means as a word, but it doesn't mean anything. But we will call these amniotes. They're the first animals to begin to lay eggs that can be laid on land. So they are very reptile-like in a lot of ways. So this is leading to the first reptiles, but we're also going to begin to sort of think about going down that mammal lineage too. So we're going to get amniotes beginning to diversify here at the end of the Pennsylvanian and at the end of the Permian. So here's some of those amniotes. Well, this guy looks still kind of amphibious. This is definitely an amphibian, a very famous one, Diplocaulus, with that kind of boomerang-shaped skull. Very cool amphibian. But we have a whole world of reptiles. During the Permian, the world is drying out because Pangea finally comes together. And when we have a big continent, the interior tends to dry out, especially with a big old mountain system, the central Pangean or Appalachian Mountains making up the middle of Pangea. That means that as air rises, making their way to the mountain system, it's going to drop a lot of rain, but then after that air mass goes over the mountains, it's dry, and that's called a rain shadow. That's why Tibet and Mongolia are so dry, is because of a rain shadow coming up over the Himalayas, dumping tons of water on India during their monsoon season, but then dry as a bone as it goes north of the Himalayas and spreads across Mongolia, creating the Gobi Desert. So that's what's happening to the whole interior of Pangea. And so it's dry. We have the West Texas Permian Basin, which is full of fossils of this reptile, not a dinosaur. This is not we're not close to dinosaurs yet. We have reptiles, but this is actually a type of reptile called a pelycosaur, and this is more closely related to our mammal ancestors than it is to a dinosaur. So yeah, sort of a kind of reptile, nothing like a dinosaur. And these go extinct at the end of the Permian, so they never even witnessed dinosaurs. They never lived at the same time as dinosaurs. So yeah, this is Dimetrodon. I know it comes as little plastic toy when you get like a dinosaur collection of toys. It's not. We can't just call every big reptile looking thing with teeth a dinosaur. It's a specific lineage on the tree of life. And we'll get into that a little bit later with the Mesozoic. But because reptiles have that amniotic egg, right? They can lay their eggs on dry land. They don't have to hang out next to ponds and rivers. They succeed and they can spread across the land. So amphibians are not going to really take off like they would have if the climate stayed nice and wet. They are going to be kind of replaced in most ecosystems by reptiles. So reptiles will be able to make their way across the landscape, inhabit every ecosystem on land, and the Permian is where reptiles really take off. Oh no, but then we have a problem. Oops. That's right. We have a big problem. We forgot. What about all that coal that we were forming? You know, you got to pay for it somewhere. So we have all this coal, and so there's a lot of things that go on that we can talk about in prehistoric life, and it'll take a while. But one of the things that happened is, first of all, we have cooling. So even though we have deserts here, there was, in many parts of the world, a kind of a gradual cooling from pulling that carbon out of the atmosphere. All right, we already talked about that. But to do that, we are creating we're creating coal, which is made up of all that carbon. Great. Well, so Pangea comes together. You can't have continents really doing a whole lot of collision and subduction, stuff like that, without having volcanoes. So we end up getting huge flood basalts, so just bodies of igneous rock, just basalt, just spreading across all of Siberia here at the end of the Permian. Turns out that there was one of the biggest coal deposits also in that part of Russia. So we are setting fire to bodies of coal here at the end of the Permian period. No humans are around to burn the coal. Doesn't matter, it's happening anyway. And so volcanoes are going to burn up a lot of that coal, taking that carbon, putting it in the atmosphere over a period of a few million years, which in geologic time is extremely fast. And during that time then, we started to get a runaway greenhouse effect. So we started to get warming of the climate because you're taking coal, putting it in the atmosphere, right? Kind of sound familiar? You know, we can learn from Earth history or not, but whatever. But anyway, that's what's going on. So we have a gradual cooling, then suddenly, bam, warming, which is so fast. That's a lot of coal in just 3 million years. That's nothing. What if you did the same amount of coal or even more in 150 years? I wonder what effect that would have. You know, that's one of the things we're thinking of. We can use the past to, start to figure out what's going on now. But anyway, so we have a big warming event, but that's not the only thing coal does. Coal also produces sulfuric acid. The burning of coal produces sulfuric acid. As we know, that produces acid rain, as happened after the Industrial Revolution. So that's also what's going on at the end of the Permian. So we have acid rain, and that's forming a lot of, we have a heavier erosion of the land from that, but that's also getting into the oceans and starting to cause a lot of disruption with the seas and the life that lives in the seas. So the warmer climate, more acid in the oceans means that shells of organisms are harder and harder to build. So all those little clams and brachiopods and things that are creating their shells out of calcium carbonate, they suffer. And so they're facing a lot of problems. Plants on land are having a hard time too. In any animal on land, there are very few species that made it through the Permian extinction event, which is also referred to as the Great Dying. So we lose, it's estimated about 95 to 96% of all life on the planet, and marine life was hit the hardest. But it rebuilds, and we'll get into that next time. So going back to our geologic timescale here, so what we covered then was, we already did that, we covered the early part of the Paleozoic, so the Cambrian to Ordovician to Silurian. We did that in the last lecture. This lecture was the Devonian through the Permian. Here's our big old extinction event. Lots and lots of different kinds of reptiles all throughout the Permian. But then for the Mesozoic, which will be the next one, we're going to see eventually the first dinosaurs and the first mammals. but the stages for those organisms have already been set here at the Permian. But then we have a big extinction event to kind of wipe the slate clean, and the Triassic is going to be kind of crazy. All right, okay, so this is a nice summary of what kind of things we've been talking about. So this is from your textbook, and I really like it because it has the time scale, Devonian through the Carboniferous, through the Permian, and by the way, here you go, you can see how they split up the Carboniferous into Mississippian and Pennsylvanian. So I could sit here and tell you what happened, but it's nice to have an image where you're like, oh, okay, I get it now. We have our sedimentary sequences, going back to our sequence stratigraphic parts or stories of North America. So we're looking at what sea level is doing over time. We have our western or Cordilleran mountain belt. That's the antler orogeny, one of the building blocks of the Rockies. But then to the east, and we're not going to see much happening here later presentations, because the Appalachians kind of finish at this point as Pangea comes together is the end of the Appalachian buildup. So we're not going to see much other eastern stuff going on. All the rest of the mountain building that we're going to see for the next few presentations, Mesozoic and Cenozoic, is going to be in the west as the Rockies continue to build. So the Appalachians are done, Rockies are just getting started here at the end of the Paleozoic. And then some evolutionary events, here we go, largest mass extinction event, but we're talking about all these other organisms. So we're kind of putting, and then some different, sedimentary bodies of rock like coal swamps, black shales, all barrier reef formations, all sorts of neat stuff going on as well. So this is a good image to tie it all together. And all I did was just kind of split it up so you could see it a bit better. So what's happening during the Devonian period, what's happening during the Carboniferous, and then again, what's happening during the Permian. So anyway, so thanks a lot for hanging out with me for a bit to talk about a really cool chapter in Earth history. So that's about, you've got a few presentations to look at. This is obviously they're all very important, but I only have 2 more, and I'll get them to you, one tomorrow, one the next day. So I'm going to get them to you as fast as possible. So Mesozoic is coming up. They're all done. It's just a matter of me taking the time to talk because, I'm not used to this, and it definitely hurts my throat. And it actually takes a couple hours to get these up on YouTube once I hit the end button. It's unbelievable. So anyway, looking forward to this and getting it up for you guys, and good luck on your final exam. Got a lot of information there, and this is definitely a big chunk of the story. So thanks a lot, and have a good rest of your day.